The next two sections are looking at empirical formulas and molecular formulas. This section, you will be able to calculate the empirical formula of a compound from the mass percent composition. The mass percent composition of methane is 74.9% carbon and 25.1% hydrogen, and it's always the same. If I add up both of these percents, they should equal 100%. So if I had 100 grams of methane, I could then say 74.9 grams of that would be carbon and 25.1 grams of that would be hydrogen. But what if I didn't have 100 grams? I wouldn't be able to just easily go, oh, 25.1% is 25.1 grams. Well, I could then just take that percent and times it by, well, if I have 25 grams of methane, I can do 25 grams times 0.251, because 25.1% as a decimal is 0.251, times that by 25 grams, and we should get 6.28 grams of that compound is made up of hydrogen. And then to find the carbon aspect, I can take 0.749 and times that by 25 grams, and we should get 18.7 grams of carbon. An empirical formula is the simplest whole number ratio of the atoms in a compound. One way of finding it is by dividing the subscripts in the actual or the molecular formula by a whole number to give the lowest ratio. For example, if I have C5H10O5, we could look at that and we could reduce 5, 10, and 5 are all able to be divided by 5. To give me 5 divided by 5 would be 1, 10 divided by 5 is 2, and 5 divided by 5 is 1. So CH2O would be the empirical formula. It's the reduced whole number ratio. Here are some examples of molecular and empirical formulas. Notice that the molecular formula is the actual formula, and in some cases we can see that the C2H2 can be reduced to just CH. 2 and 2 are both divisible by 2 to make it 1 and 1. So the empirical formula is the simplest form. So C2H2 can be reduced to CH. Benzene, C6H6, can also be reduced to CH. Notice that ammonia, NH3, there's one N and three H's. That can't be reduced anymore. So in some cases, the empirical formula is the same as the molecular formula. Here we have N2H4, 2/4 can be reduced to 1/2, so NH2. We already looked at this one, C5H10O5 are all divisible by 5, so CH2O. And then glucose, C6H12O6, are all divisible by 6. So that can be reduced to the same as ribose. Let's look at a sample problem. Iron and chlorine make up a compound that's used to purify water in water treatment plants. We want to find the empirical formula of a compound if experimental analysis shows that a sample of the compound contains 6.87 grams of iron and 13.1 grams of chlorine. Whenever we're given grams of something, we need to get to moles. And in order to do that, we have to look at our periodic table and we have to say, well, how many grams of iron is in 1 mole of iron? And 55.85 is what our periodic table should show us. So we have to have grams on the bottom because we have grams that we're starting with. So what do we want? We want moles. What have we got? We've got gram. The grams and grams are going to cancel, so we can see our moles of iron. We're going to do the same thing with chlorine. We need our grams of chlorine on the bottom, 35.45 grams of chlorine and 1 mole of chlorine. That'll cancel out our grams, leaving us with 0.370 moles of chlorine. Now we obviously can't write a compound that says Fe 0.123 and Cl 0.370. We need whole number ratios. And in order to get a whole number ratio, we want to divide both of these by the smaller of the two numbers. And the smaller of the two would be 0.123. So if I did 0.123 divided by 0.123, that's going to give me 1. Now we have to see, what does 0.370 divided by 0.123 give me closest to the nearest whole number? And we would see that we would get 3.01, which we can round to 3. It's close enough to round to 3. Fe1CO3 would be written as FeCO3. That is our empirical formula. All we did was go grams to moles, and then we divided both of those moles by the smaller of the two numbers to get whole number ratios. Let's look at a second example. Tetrafluoroethene is a colorless liquid used for dry cleaning. What is the empirical formula if its mass composition is 14.5% carbon and 85.5% chlorine? Whenever we're given percents, again, both of these would add up to 100. We're going to assume that we have a 100-gram sample of the two of them. And so I'm going to say that I have 14.5 grams of carbon and 85.5 grams of chlorine. And if I start with grams of each of those, we know we can go grams to moles using the molar mass. Make sure that you have the grams on the bottom again because we need the grams to cancel out. Go grams to moles, leaving me with 1.21 moles of carbon and 2.41 moles of chlorine. And just like that last example, I can't write 1.21 and 2.41 for subscripts. I need whole number ratios. So we're going to divide both of these by the smaller number, which in this case is the 1.21. So divide both by 1.21, that will give me 1 carbon, and that should give me 2.4 divided by 1.2 should give me 2, or 1.99 is what your calculator would say, and we can round that to 2. So we would have CCl2. In both of those examples, our numbers were really close to a whole number. For example, 2.02 we can round to 2. 6.98 we can round to 7. However, if we have a decimal that's greater than 0.1 or less than 0.9, we should not round it. Instead, we would multiply however many elements were in that compound when we got done by dividing everything by the smaller number. We would multiply all of them by a number to get that decimal point to the nearest whole number. For example, let's say I divided everything by, like this last one, let's say I divided everything by 1.21, and instead of getting the 1.99, let's say I got 1.2. Well, if I multiplied that by 5, 1.2 by 5, I would get a whole number. So I would do that to all of the elements. Same with if I got something 0.25, I would multiply it by 4 to get a whole number. If something was 0.33 and I multiplied it by 3, I would get a whole number. Obviously, if something came out as 0.5, we just have to times it by 2, and 0.67, if we multiplied it by 3, would get to a whole number. Let's do one more sample problem. We have ascorbic acid, which is vitamin C, found in citrus fruits and vegetables. It's important in metabolic reactions in the body, in the synthesis of collagen, and in the prevention of scurvy. If the mass percent composition is 40.9% carbon, 4.58% hydrogen, and 54.5% oxygen, what is the empirical formula? Again, if I know percentage, I'm going to put that into grams. And if I know grams, I can go to moles by looking at the periodic table and finding the molar mass for each one of those. It will give me how many moles of carbon, hydrogen, and oxygen. The next step is to divide each one of these by the smallest number. And 3.41 seems to be the smallest for both of these guys. So divide these by 3.41. That'll give me 1 and 1. And 4.54 divided by 3.41 should give me 1.33 moles of H. This is one of those cases where I don't want to round it down to 1. How do I get 1.33 to the nearest whole number? Well, I need to multiply everything by 3. 1.33 times 3 would give me 4. 3 times 1 is obviously 3. 3 times 1 is 3. That will give me my lowest whole number ratio of moles as subscripts. That wraps up this section, so take a minute to check the learning goal, make sure that you feel comfortable with it. The last section of the chapter is about molecular formulas. You will be able to determine the molecular formula of a substance from the empirical formula and the molar mass. An empirical formula represents the lowest whole number ratio of atoms in a compound. You know that, we just did that last section. A molecular formula represents the actual numbers of atoms in a compound. So molecular formula, we need to take a integer, 1, 2, 3, 4, and then we times that by the empirical formula. Here's a chart showing all of the different compounds that have the same empirical formulas. But notice that the molecular formulas are all different. They're all multiples of this empirical formula. So if I take the molar mass and multiply it by 1, I would get the same molecular formula as the empirical formula. Now let's say that my molar mass doubled. That means I need to multiply everything in my empirical formula by 2. If it's tripled from the original, then I would multiply everything by 3. And then you can see If I have a mass of 120.12, that's 4 times my empirical formula and 5 times the empirical formula. So you take everything in that empirical formula and multiply each element by that integer. Once we determine the empirical formula of a compound, we can calculate its mass in grams. Given the molar mass of the compound, we can calculate the value of that integer by taking the molar mass of the compound divided by the empirical formula mass. That should give us really close to a whole number integer. For example, when the molar mass of ribose is divided by the empirical formula mass, so we took that ribose, that 150.15, and we divided it by the formula mass of 1 carbon, 2 H's, and 1 O, which is 30.03, we got 5. We then took 5 and times it by everything in CH2O, giving us C5H10O5. Let's look back at that vitamin C, ascorbic acid, C3H4O3. The molar mass of its molecular formula is 176.12 grams per mole. In order to find out the molecular formula, we need to take the molecular formula's mass, the 176.12, and divide it by the empirical formula's mass. So we need to add up 3 carbons, 4 H's, and 3 oxygens, which they did right here. 3 carbons, 4 hydrogens, 3 oxygens, and they got 88.06 grams. When we do 176.12 divided by 88.06, we get 2. That means in order to find the molecular formula, we take everything in the empirical formula and times it by 2, giving us C6H8O6 for the molecular formula. Let's do another example. Melamine, which is used to make plastic items such as dishes and toys, contain 28.57% carbon, 4.80% hydrogen, and 66.64% nitrogen. If the experimental molar mass is 125 grams, what is the molecular formula of melamine? All right, this 125 grams is going to come into play in a minute when we get to this part to find that small integer. That's the molar mass of the melamine. We need to take that and we'll divide it by the empirical formula mass as soon as we find it. First, we need to find out what the empirical formula is. We want to take all of these percents and put them into grams. So we have grams of carbon, hydrogen, and nitrogen. And if I have grams, I can get to moles. These are all straight from the periodic table telling us the molar mass of carbon, hydrogen, and nitrogen. That gave us the 2.38 moles of carbon, 4.76 moles of hydrogen, 4.76 moles of nitrogen. We need to divide everybody by the smallest ratio, which would be that 2.38. Giving us 1 mole of carbon, 2 moles of H, and 2 moles of N. Therefore, CH2N2 is our empirical formula. Now we need to find the empirical formula's mass. Let's add up 1 carbon, 2 H's, and 2 N's. That'll give me the empirical formula mass of 42.05. Now we can find out what that integer is and take that 125 grams that we were told for the molar mass divided by the empirical mass, and we got 2.97, which is really, really close to 3. That means we're going to take that empirical formula and we're going to times everything by 3. 1 times 3 would be 3, 2 times 3 is 6 and 6, giving us the molecular formula for melamine. That wraps up this chapter. Take a minute to look at the learning goal to make sure you feel confident about it. And here is the concept map from Chapter 7. I've got a bunch of practice problems for you. Be sure that you are pausing the video to do the self-test problems before you look at the answers that are at the bottom. Here's another set of 2. Again, cover up the answers. Make sure that you are trying. Another set of 2. Here's converting between moles and grams. Converting between mass and moles. This one's converting between grams of a compound and grams of an element. This one is looking at mass percent composition. This one is calculating an empirical formula. Another one looking at empirical formula. Another empirical formula. and finally looking at molecular formulas. As always, if you have any questions, please feel free to email me and I can work out any of these problems to show you my step-by-step process.